A covalent bond, also called a molecular bond, is a chemical bond that involves the sharing of electron pairs between atoms. These electron pairs are known as shared pairs or bonding pairs, and the stable balance of attractive and repulsive forces between atoms, when they share electrons, is known as covalent bonding. For many molecules, the sharing of electrons allows each atom to attain the equivalent of a full outer shell, corresponding to a stable electronic configuration. Covalent bonding includes many kinds of interactions, including sigma bonding, pi bonding, metal-to-metal bonding, agostic interactions, bent bonds, and 3-center two-electron bonds. The term covalent bond dates from 1939. The prefix co means jointly, associated in action, partnered to a lesser degree, etc. Thus a covalent bond, in essence, means that the atoms share valence, such as is discussed in valence bond theory. In the molecule H2, the hydrogen atoms share the 2 electrons via covalent bonding. Covalency is greatest between atoms of similar electronegativities. Thus, covalent bonding does not necessarily require that the two atoms be of the same elements, only that they be of comparable electronegativity. Covalent bonding that entails sharing of electrons over more than 2 atoms is said to be delocalized. History. The term covalence in regard to bonding was first used in 1919 by Irving Langmuir in a Journal of the American Chemical Society article entitled, "The Arrangement of Electrons in Atoms and Molecules." Langmuir wrote that, "We shall denote by the term covalence the number of pairs of electrons that a given atom shares with its neighbors." The idea of covalent bonding can be traced several years before 1919 to Gilbert N. Lewis, who in 1916 described the sharing of electron pairs between atoms. He introduced the Lewis notation or electron dot notation, a Lewis dot structure, in which valence electrons are represented as dots around the atomic symbols. Pairs of electrons located between atoms represent covalent bonds. Multiple pairs represent multiple bonds, such as double bonds and triple bonds. An alternative form of representation, not shown here, has bond-forming electron pairs represented as solid lines. Lewis proposed that an atom forms enough covalent bonds to form a full outer electron shell. In the methane diagram shown here, the carbon atom has a valence of 4 and is therefore surrounded by 8 electrons, 4 from the carbon itself and 4 from the hydrogens bonded to it. Each hydrogen has a valence of 1 and is surrounded by 2 electrons, its own 1 electron plus 1 from the carbon. The numbers of electrons correspond to full shells in the quantum theory of the atom. The outer shell of a carbon atom is the n equals 2 shell, which can hold 8 electrons, whereas the outer shell of a hydrogen atom is the n equals 1 shell, which can hold only 2. While the idea of shared electron pairs provides an effective qualitative picture of covalent bonding, quantum mechanics is needed to understand the nature of these bonds and predict the structures and properties of simple molecules. Walter Heitler and Fritz London are credited with the first successful quantum mechanical explanation of a chemical bond in 1927. The work was based on the valence bond model, which assumes that a chemical bond is formed when there is good overlap between the atomic orbitals of participating atoms. Types of covalent bonds. Atomic orbitals have specific directional properties leading to different types of covalent bonds. Sigma bonds are the strongest covalent bonds and are due to head-on overlapping of orbitals on 2 different atoms. A single bond is usually a sigma bond. pi bonds are weaker and are due to lateral overlap between p orbitals. A double bond between two given atoms consists of 1 sigma and 1 pi bond, and a triple bond is 1 sigma and 2 pi bonds. Covalent bonds are also affected by the electronegativity of the connected atoms, which determines the chemical polarity of the bond. Two atoms with equal electronegativity will make non-polar covalent bonds such as HH. An unequal relationship creates a polar covalent bond such as with H-Cl. Covalent structures. There are several types of structures for covalent substances, including individual molecules, molecular structures, macromolecular structures, and giant covalent structures. Individual molecules have strong bonds that hold the atoms together, but there are negligible forces of attraction between molecules. Such covalent substances are usually gases, for example hydrogen chloride, SO2, CO2, and CH4. In molecular structures, there are weak forces of attraction. Such covalent substances are low boiling temperature liquids, and low melting temperature solids. Macromolecular structures have large numbers of atoms linked by covalent bonds in chains, including synthetic polymers such as polyethylene and nylon, and biopolymers such as proteins and starch. Network covalent structures contain large numbers of atoms linked in sheets, or three-dimensional structures. These substances have high melting and boiling points, are frequently brittle, and tend to have high electrical resistivity. Elements that have high electronegativity, and the ability to form 3 or 4 electron pair bonds, often form such large macromolecular structures. 1 and 3 electron bonds. Bonds with one of 3 electrons can be found in radical species, which have an odd number of electrons. The simplest example of a 1-electron bond is found in the dihydrogen cation, H+. 2. 1-electron bonds often have about half the bond energy of a 2-electron bond, and are therefore called half bonds. However, there are exceptions. In the case of dilithium, the bond is actually stronger for the 1-electron Li+2 than for the 2-electron Li2. This exception can be explained in terms of hybridization and inner shell effects. The simplest example of 3-electron bonding can be found in the helium dimer cation He+2. It is considered a half bond because it consists of only one shared electron. In molecular orbital terms, the third electron is in an anti-bonding orbital which cancels out half of the bond formed by the other 2 electrons. Another example of a molecule containing a 3-electron bond, in addition to 2 2-electron bonds, is nitric oxide, NO. The oxygen molecule, O2, can also be regarded as having 2 3-electron bonds and 1 2-electron bond, which accounts for its paramagnetism and its formal bond order of 2. Chlorine dioxide and its heavier analogues, bromine dioxide and iodine dioxide, also contain 3-electron bonds. Molecules with odd electron bonds are usually highly reactive. These types of bond are only stable between atoms with similar electronegativities. Resonance. There are situations whereby a single Lewis structure is insufficient to explain the electron configuration in a molecule. Hence, a superposition of structures are needed. The same 2 atoms in such molecules can be bonded differently in different structures, resulting in a non-integer bond order. The nitrate ion is one such example with 3 equivalent structures. The bond between the nitrogen and each oxygen is a double bond in one structure and a single bond in the other 2, so that the average bond order for each NO interaction is 2 + 1 + 1/3 equals 4/3. Aromaticity in organic chemistry. When a molecule with a planar ring obeys Huckel's rule, where the number of pi electrons fit the formula for n + 2, it attains extra stability and symmetry. In benzene, the prototypical aromatic compound, there are 6 pi-bonding electrons. These occupy 3 delocalized pi molecular orbitals or form conjugate pi bonds in 2 resonance structures that linearly combine, creating a regular hexagon exhibiting a greater stabilization than the hypothetical 1,3,5 cyclohexatriene. In the case of heterocyclic aromatics and substituted benzenes, the electronegativity differences between different parts of the ring may dominate the chemical behavior of aromatic ring bonds, which otherwise are equivalent. Hypervalence. Certain molecules such as xenon difluoride and sulfur hexafluoride have higher coordination numbers than would be possible due to strictly covalent bonding according to the octet rule. This is explained by the 3-center 4-electron bond model, which interprets the molecular wave function in terms of non-bonding highest occupied molecular orbitals in molecular orbital theory and ionic covalent resonance in valence bond theory. Electron deficiency. In 3-center 2-electron bonds, 3 atoms share 2 electrons in bonding. This type of bonding occurs in electron-deficient compounds like diborane. Each such bond contains a pair of electrons which connect the boron atoms to each other in a banana shape, with a proton in the middle of the bond, sharing electrons with both boron atoms. In certain cluster compounds, so-called 4-center 2-electron bonds also have been postulated.